chart, problems on basic applications of Smith chart, series on transmission line theory, lecture number 4.21. Smith chart is a graphical tool. It is widely used for solving problems in transmission line theory. It is useful to determine standing wave ratio over the line. It is useful to find reflection quotient, line impedance, load impedance, locations of voltage minimum, voltage maximum points, and it is also used for several other purposes. In the present session, the focus is on problems set around basic applications of Smith chart in solving problems. To begin with, let us consider a problem. Using Smith chart, determine impedance at point P and SWR over the line when RC over the line at P is gamma is A 0.25 30 degrees, B gamma is 0.60 at minus 45 degrees. So the problem is reflection coefficient is given and we are asked to find out impedance and also SWR over the line. Solution. In each case, draw radial vector from center of chart O to periphery Q at an angle equal to angle of RC. Then locate point P over the radial vector satisfying OP equal to magnitude of reflection quotient multiplied by OQ. In case A, O is center of the chart and a radial vector is drawn at an angle equal to angle of reflection quotient. In this case, it is 30 degrees. So at 30 degrees, a radial vector is drawn. This radial vector cuts the periphery at Q. Now over this vector we have to locate a point P such that OP is equal to 0.25 times OQ. So now P is available. Coordinates of P give normalized impedance. Point P is associated with a circle and an arc. Circle gives resistance and arc gives reactance. So impedance can be read out from point P. To find SWR, draw SWR circle through point P. So this is SWR circle CC. This circle cuts right half of the horizontal line at a point here. Corresponding to this point, there exists a reading that is SWR. In this case, it is 1.67. In case of B, gamma is 0.60, angle is minus 45 degrees. So what we have to do is draw a radial vector from center of the chart to the periphery at an angle of minus 45 degrees. So this is the line OQ, and over this radial vector locate point P such that OP is equal to 0.6 times OQ. So point P is now available. P is associated with certain impedance. That impedance one can read out from the circle that is passing through point P and also the arc that is passing through this point P. Now impedance is available. This is normalized impedance. Through point P one can also draw a circle, SWR circle. This SWR circle cuts right half of the horizontal line at a point. This point is associated with certain reading. It gives you SWR. We consider another problem. Using Smith chart, determine locations of first Vmax and Vminimum on the source side over a lossless line from a point where line impedance A ZL is 0.9 minus J2, B ZL is 3 plus J.2. Work out the problem to find their locations on load side. Obtain results analytically and cross-check. Here we are asked to determine locations of first Vmax and Vminimum from source side and impedances are given. Solution process. Locate load point over the chart and draw radial vector OPQ from center to periphery. See, ZL is given in both the cases A and B. ZL is available. From ZL one can locate load point. See, in case of A, this is load point ZL. From ZL, draw radial vector. OPQ is the radial vector. Measure the distance of this vector to right and left half of horizontal axis to get distances of first Vmax and first Vminimum. So from this radial vector, one can measure the distance using the scales available over the periphery, this distance, one distance comes out 0.186 lambda. That is distance of V minimum. And another distance is 0.436 lambda. This is distance of V max. So the measurement is clockwise. So it is on the source side. Source side, first V minimum, first V maximum are at a distance of 0.186 lambda. V max is at a distance of 0.436 lambda from the load point. If the measurement is clockwise, it is the source side. Here measurement is done here in this diagram, first diagram, measurement is done in clockwise. So it is source side. If we want load side, then we have to measure the distances anti-clockwise. Anti-clockwise measurement gives V max distance equal to 0.064 lambda from load point and 0.314 lambda for V minimum from load point. This is as far as A. B, same procedure. In case of B also, first we have to look at load point. This is load point. And to draw radial vector, this is radial vector. And measure the distance of this from this radial vector, right half of the horizontal axis. It gives V max, distance of V max in clockwise direction. And measure distance of left half of horizontal axis. It gives V minimum from the load point. In the present case, it is 0.025 lambda, 0.275 lambda. These are distances of V max point and V minimum point from load point on source side, because measurements are done in clockwise direction. If you measure in anti-clockwise direction, they are shown in the last diagram. V minimum point is at a distance of 0.225 lambda. Maximum point is at a distance of 0.475 lambda. This is load side case. Analytically, also one can do it. In case A, the RC gamma L corresponding to line impedance ZL is evaluated. Gamma L is this one. It comes out 0.726 at an angle of 0.81 radians. It is negative. Load is capacitive and hence location of V minimum on the source side is lambda pi plus theta L by 4 pi. It comes out 0.186 lambda. Location of V max is location of V minimum plus lambda by 4. So it comes out 0.436 lambda. On the load side, in the similar manner, locations of V max and V minimum can be found 0.064 lambda, 0.314 lambda. In the same way, one can evaluate the distances of V max, V minimum, source side, load side too, by following the same procedure. First, we have to obtain gamma L, angle is positive, so it is inductive. Location of V max is lambda theta L by 4 pi, which is equal to 0.25 lambda. Location of V minimum is at a distance of quarter wavelength further away. So it comes out 0.275 lambda. On load side, locations of V max and V minimum become 0.475 lambda and 0.225 lambda. Now another problem. Using Smith chart, determine SWR and RC over the load. SWR over the line, RC over the load. When a normalized load impedance admittance is, see in A, normalized load impedance is given. In B, normalized admittance is given. Work out the problem analytically and compare the results. Now, locate normalized load impedance or admittances over the chart and let it be P, load point. We have to locate. In A, load point is somewhere here, P. Now, in case of B, load point is here somewhere. You can see. Now draw SWR circle in each case, and this circle cuts the horizontal line of the chart at 2 points. In case of A, it cuts at 6.25. Therefore, in this case, SWR is 6.25. In case B, it cuts horizontal axis at 3.13. Right half of the horizontal axis. So 3.13 is the SWR in this case. One on left half of the center PL and other on the right of the center PR. The point on the right of the center gives required SWR. Okay. So that way SWR can be found. In each case, draw radial vector from center of the chart to O to periphery Q through P. So here this radial vector is drawn. Here also radial vector is drawn. Measure ratio OP to OQ. With a scale, one can measure the distance OP OQ and consider the ratio. This ratio gives magnitude of RC. Angle of RC can be found from the peripheral scale in the chart. In case of admittance, plus or minus 180 degrees is to be added to the measured angle. So in this case, one has to add plus or minus 180 degrees as is required. From the chart, one can see in case of A, rho SWR is 6.25 and magnitude of reflection coefficient can be found as 0.725. Angle is 66.46 degrees in case of A. In case of B, this is reflection coefficient. Reflection coefficient rho is 3.12. Magnitude is 0.516. Angle is 10 minus 180 degrees, that is minus 170 degrees. We have to use negative 180, minus 170 degrees. Now, working out the problem analytically, gamma L is ZL minus 1 by ZL plus 1. So this is a reflection coefficient. And rho is SWR is 1 plus gamma by 1 minus gamma. So 6.25. 6.25, it is tallying with 6.25. Magnitude and angle is tallying with. In the same way, B, in case of B also, one can find out gamma and SWR. And also one can notice they are tallying with the results obtained using Smith chart. Another problem. Using Smith chart, determine impedance over a lossless line at a distance of lambda by 6, load side, and lambda by 12, source side from a point where normalized impedance is A. ZL is 0.9 plus J2. B. ZL is 3 minus J.2. The line is there is a point P. At this point, line impedance is given. Slightly away from this point, source side, what is impedance? Load side, what is the impedance? This is the problem. How to solve it? Simple. Solution. Locate the given load over the chart, draw SWR circle, move lambda by 6 counterclockwise direction over it to find line impedance there. To find line impedance at a distance of lambda by 12 source side on the line, move clockwise. So first what we have to do is ZL is available. From ZL, locate the point. This is the point. Somewhere here, yes, this is the point. Point P. This is from ZL, given ZL, this point P can be located. Similarly, here also in case of B also, locate point P. Now, from ZL, draw SWR circle. CC is SWR circle. Here also CC is SWR circle. Move lambda by 6 counterclockwise direction. So, from point P, move a distance of lambda by 6. Using the scale that is available over the periphery, move a distance, lambda 6. So, you will come here, somewhere here. So, this point denotes certain impedance. Read out that impedance. That impedance gives the line impedance, load side, at a distance of lambda by 6 from the point P. If you want impedance over the line at a distance of lambda by 12 towards source side, then you have to make a movement clockwise like this, clockwise, lambda by 12. To reach a point P, this point represents a certain impedance. That impedance can be read out. That impedance represents impedance at a distance of lambda by 12 source side from the load point on the line. Same is the case when line impedance is ZL is 3 minus J 0.2. That is in case of B, Q, same thing. In case of A, in case of A, ZL, this is ZL at lambda by 6 load side, and ZL, it is at lambda by 12 source side, at a distance of lambda by 12 towards source side. So in case of B, see, these are the results which were obtained from the Smith chart. To work out analytically, the RC gamma L corresponding to line impedance ZL is to be evaluated. So this is gamma L. Okay. ZL is available, so gamma L can be at a distance of lambda by 6. Lambda by 6 corresponds to 2.09 radians. Load side, phase angle RC becomes 0.81. See, this is 0.81 plus 2.09 radians, and at a distance of lambda by 12. Lambda by 12 means 1.047 radians. So, source side phase angle of gamma is 0.81 minus 1.047. So, it gives minus 0.2237. As the line is lossless, magnitude of RC over the line is constant. Hence, at a distance of lambda by 6 load side, impedance becomes this. It can be found tallying with the thing that is obtained from Smith chart. At a distance of lambda by 12, source side impedance can be found. This is the basic relation. It doesn't require an explanation. Similarly, for B also one can find line, ZL load side, ZL source side 2. Another problem, using Smith chart, determine load impedance or line impedance ZL at point P at a distance of lambda by 5 source side and a distance of lambda by 10 load side. Here load side. When RC over point P is, here RC is given. Two cases are given, A, B. In both the cases, gamma is given at a point P. This is a line at a point P. Gamma is given. We considered source side a point, load side another point. Source side point is at a distance of lambda by 5. Load side, the point is at a distance of lambda by 10. We are asked to find out impedance. This problem is very much similar to the problem which we solved in the previous case. Solution. In each case, draw radial vector from center of the chart to periphery Q at an angle equal to angle of RC. See, in both the cases, angle of RC is available. Take the Smith chart and draw. Here it is minus 60 degrees in case of A. In case of B, it is 30 degrees. Minus 60 degrees means somewhere here. So from here, draw the radial vector. In this case, 30 degrees. From here to here, draw. Locate point P over the radial vector satisfying OP equal to gamma magnitude into OQ. So P comes into picture. P comes into picture. This is load point. Now from here, the solution process is same as that which we had in the previous problem. The coordinates of this point gives ZL and then move lambda by 5 clockwise from load point over the circle to locate a point. Its coordinates gives Z lambda by 5. Next move lambda by 10 anti-clockwise from load point over the circle to locate a point. Its coordinates give Z lambda 10. Note when the point where we want impedance is on load side, movement is anti-clockwise. When the point where we want impedance is on the source side, then the movement is on clockwise. For A, from chart, it can be found ZL at P. ZL is 1.105 minus J 0.911. This ZL is not given, but we can read out if you want. We can read out the coordinates of point P. That gives impedance. So ZL is 0.44 plus J 0.172 at lambda by 5 source side. ZL is 2.226 plus J 0.44 at lambda by 10 load side. Similarly for B also. In this case also process is same. Okay. Now the problem is solved analytically. Firstly, let us determine ZL at point P. We are given reflection quotient at point P. From reflection quotient, impedance ZP equal to 1 plus gamma P by 1 minus gamma P. It comes out 1.105 minus J 0.911. At distance of lambda by 5, lambda by 5 corresponds to an angle of 2.513 radians. Phase angle of RC on source side is minus 1.047. Note, this is angle of reflection quotient, radians. Lambda by 5 gives an angle of 2.513 radians. Together minus 3.56 radians. And at a distance of lambda by 10 corresponds to 1.256 radians. Phase angle of gamma is minus 1.047 plus, here it is plus, reason is it is load side. So it comes out angle of gamma as 0.209 radians. As the line is lossless, magnitude of RC over the line is constant, hence distance of lambda by 5. At a distance of lambda by 5, load side impedance becomes this. Magnitude is known, angle is computed, so ZL one can find out within no time. 0.44 plus J 0.172. This is the value of ZL over the line at a distance of lambda by 5 on load side. At a distance of lambda by 10, in the same way one can find out ZL. It comes out to be equal to 2.226 plus J 0.44. Similarly for B also, one can do the same exercise and find out ZL. Now we consider another problem, impedance. A 75 ohm lossless line is terminated on a load with impedance 100 plus J 150 ohms. Consider impedances A, B, C. Three impedances are given, and using Smith chart determine whether the given impedances can be over the line. If they are over the line, find the distances of these impedances from the load. So a line cannot have all types of impedances. It can have only certain impedances. We are asked to find out whether the given impedances can be over the line or not. Solution. Locate load impedance ZL over the chart and then draw constant SWR circle. ZL is 100 plus J 150. This is load impedance and it has to be normalized. Smith chart works only with normalized impedances. Normalization results in 1.33 plus J2. ZA, normalized impedance given in A is 0.47 plus J 0.63. This one we got by dividing 35.50 plus J 47.25 with the characteristic impedance of the line. Similarly, ZB, ZC also one can compute. Locate the given line impedances and out of all, only those which fall over the SWR circle can represent impedance over the line. So what we have to do is, first we have to locate load impedance here and we have to draw SWR circle, that is CC, and we have to locate then ZA, ZB, ZC. You see here ZB is here, ZA, this is ZC. Out of these three, only ZB is over the SWR circle. Therefore, ZB only can be over the line. ZA, ZC cannot be there. Now to find the location of the impedance ZB, what we have to do is we can measure the distance between ZL and ZB clockwise. Clockwise means source side. From the Smith chart, the distance between load point to point when impedance is equal to given can be found as 0.4 lambda. Another problem, a 50 ohm lossless line is connected to an unknown impedance giving a maximum voltage of V max equal to 0.90 volts and a minimum voltage of V minimum equal to 0.45 volts over the line. When the load is replaced by a short, the shift in minima is found as 0.15 lambda towards source. Using Smith chart, find load impedance. What is the process? What is the procedure? From V max, V minimum, one has to find out SWR. V max by V minimum, SWR 2. Now, with this SWR, one can sketch SWR circle over the Smith chart. Now, theta L can be found. What is theta L? It is angle of reflection quotient over the load. This theta L can be found 4 pi by lambda into this displacement towards source 0.15 lambda minus pi. It comes out 0.40 pi radians. From this, one can locate the load point. So this is the load. This is the reflection quotient angle. This one becomes reflection quotient angle. Not only that, it is shifted towards the source. Minima shifted towards the source, 0.15 lambda. So this also, this distance also becomes 0.15 lambda. Either way, first one can find out theta L. From theta L, ZL can be located, or using 0.15 lambda by taking a distance, one can locate ZL, point P, which represents ZL. Once ZL is located from its coordinates, ZL can be found. That is one way. Another way is from gamma L, theta L, ZL also can be found. So this is analytical means. Graphical means locate ZL. Simply read out the coordinates of the point and multiply it with 50 ohms. These are some of the points which I want to share with you right now regarding applications of Smith chart in solving different problems in transmission line theory. Enough for now.